So we're going to look at an actual example of parabolic motion in a specific instance. So let's say you and your friend are playing catch. Let's say like on average you throw a ball at 45-degree angle with enough force to give it an initial velocity of 10 meters per second once it leaves your hand, right? So if your friend, who we'll say is about your height, is 10 meters away, assuming they don't move, so they can't like run forward or backwards to catch the ball, will they be able to catch the ball before it lands? And we're going to assume also no air drag. So to answer a problem like this, it's two-dimensional kinematics. We're going to break it into two one-dimensional problems, both the horizontal and the vertical. And what we are also going to look at is an acronym for problem solving that I've kind of come up with. You might have heard of others. This is one that I personally use. I like. It's called, I call it FIDESA. It's just an easy way to remember it. The F in FIDESA, so that's our first letter, stands for find. And that would be exactly what I'm looking for. So in this case, I'm going to either be looking for a comparison of times or a comparison of distances. And what I think I'm going to do is I'm going to use a comparison of distance with either the 10 meters away in comparison to whatever distance I come up with when I plug in my equations. So I'm going to specify and compare the distances. And that'll make more sense as we go on, right? But like that's essentially what I would denote for my find. And the reason to do that is to essentially reassess and be like, okay, what is my end goal, my result? What am I looking for? The next letter in the acronym for FIDESA is I. I stands for image. And this is just drawing out what's going on in our situation. And for this specific case, I'm going to draw it out on an XY graph, just so we can see the vertical and the horizontal components, put them in terms of Cartesian coordinates. So we've got our vertical and our horizontal, we'll say X. And I'm going to set our vertical components, our initial height, at where me and my friend are when we throw and catch the ball. So we're going to kind of set the ball as starting from the same height that it is caught at. So that's I'm going to denote as my Y0. So the ball starts here. I'm also going to denote my position as just the origin, 0, 0, in terms of the horizontal and the vertical. So it's going to start here and it's going to come here. So it's either going to reach my friend. So let's call this me or you. This would be our friend. And it's either going to reach our friend or we're saying maybe it falls too short and doesn't reach our friend. This is some X final position it could fall through. Or we're saying the opposite. Maybe it goes so high up that my friend can't catch it. Like they're not even tall enough to jump or they're just too lazy or whatever. And it goes here and lands here, right? So we're trying to compare this and kind of put it into context there. So that would be like a valid image for essentially what's going on in this problem. So it could follow a few, and those are not the only three it could follow. It could follow more of it. The D stands for data. And this is essentially the values you're given in your problem. So in this case, I know that my angle theta is 45 degrees. My initial velocity is 10 meters per second. I know that my friend, so we'll say X final, we're going to specify this, that the distance of my friend is going to be, well, maybe let's not denote it as XF. I'm going to literally just write out X friend as equal to 10 meters away, so as to not confuse it with X final. And I'm going to set my X initial and my Y initial as 0, because I said I'm at the starting origin, right? So Y initial is equal to 0 meters, X initial is equal to 0 meters. I'm going to specify one more thing, too, in this case, that my Y final, when it reaches my friend, should also be the same 0 meters. But we'll take a look at that here in a second to kind of assume essentially how long it would take if it did reach my friend. So yeah, we're going to specify that the y final is also 0 meters if it were to reach my friend. So essentially, how long would it take to follow or to go past that distance, so to speak? So that's going to be D for my data. The next letter in the acronym FIDESA is E. E stands for equations. And there's really 3 that I'm going to want to be using. I want to know that the x component for a vector component is equal to the radius times the cosine theta. The y component is equal to the radius times the sine theta. And I want the kinematic equation x final equals x initial plus v initial t plus 1/2 a t squared. Okay. So those are my equations. The next letter in FIDESA is S. S stands for solution. And this is the algebraic expression. So no numbers at this point still. We get one final equation, and then at the very end, we'll plug in numbers to get an answer. So the solution is not the same as the answer. And the reason why we do this, to solve everything algebraically first, it can be frustrating and annoying at first. But once you get used to it, it's actually very nice. And the reason we do it is for if you ever code anything in physics, it's so much easier if you make a mistake or you want to adjust parameters to just change a few inputs rather than have to change lines of code where you've done your calculations. So by calculating everything algebraically, we make it so we have to do less work interchangeably over in the end. So my solution essentially for this set, I'm going to use the kinematic equation, but we're going to modify it a little bit. So far, we've only ever looked at the kinematic equation in terms of one dimension, and we're going to need to break it down a little further than that. So the vectors, velocity and acceleration, they're vectors, so they're direction specific. So if I want to put it in terms of 2 dimensions, I'm going to look at the horizontal, we'll call the x, and the vertical, we'll call the y. So let's do the horizontal. This is going to be everything in terms of x. I have x final. I'm just going to keep the x's there since that's still the horizontal. That's equal to x initial plus, instead of v initial, I need the x component of the velocity. So I'm just going to denote that as v initial x, and we'll substitute the value in for it later, times time plus 1/2 acceleration, also vector. So I need acceleration x times time squared. So those are different. And then for the vertical, let's call this the y. So I'd have y final is equal to y initial plus this would be v initial y t plus 1/2 the a acceleration in the y direction times time squared. And both are applicable. The equation is still roughly the same. The physics principles are there and true. We've just now denoted them in their specific directions. All right. Before I start plugging in further equations into the solution, I'm going to move just stuff around so we have more space for our actual solutions to undertake. The first thing I'm going to do is I want to figure out how much time is it going to take for my ball to essentially leave my hands and get down to the same height of where it started, right? So I'm going to essentially think of it like this. What is the time increment to get vertically from where it leaves my hands back to roughly that same height? So it's not going to like hit the ground, so to speak, but that's about how long it would take to get to the height. And then I can use that time to figure out how much or how far it's gone vertically is what I'm going to do, because I don't really have a time increment here. So I'm going to use the vertical equation first. I'm going to note some very specific things. So I'm going to use y final equals y initial, v initial y t plus 1/2 ay t squared. And let's also denote what is the acceleration in my vertical direction. It's gravity. Once it leaves my hands, there's actually only one acceleration, one force acting on it, and that is gravity. So it's gravity pulling it down. And we're going to denote that, right? So gravity is equal to, it's important that this should be negative 9.8 meters per second squared. And that's essentially going to be my a sub y. So then my y final, I'm going to move the y initial to the other side. So I'm going to call it minus y initial. That is equal to v initial y time plus 1/2. Instead of writing acceleration In the y direction, I'm going to write g, so that's what the acceleration is, times time squared, okay? If I say that it starts at a height of 0, which technically it doesn't, it starts at my height, but remember, we can set our coordinate system to whatever we want. So it starts at a height of 0, and I want to see how long it takes to get back down to that same height. This is essentially going to be 0 minus 0, so both goes to 0. And my displacement is just 0, right? So then I'm saying that my initial velocity in the y direction times time plus 1/2 gt squared is going to be equal to 0. So I'm going to set that up. I'm also going to specify one more thing. So I'm going to, all right, so let's rewrite it. 1/2 gt squared plus, instead of writing VIY, so the initial velocity in the y direction, well, what is that? In terms of vectors, that's the radius times the sine. All right, so I'm going to use that as the radius would be the whole velocity. So VI, then sine theta. That's my VI. That's my initial component in the y direction. Times time. And that's my equation, right? So that's going to be set to equal 0. This you can think of as a quadratic. I'm going to factor out the t's. Now you might be thinking, well, aren't you going to get 2 values for time? This is a model. So, right, the equation models the real life example. It doesn't have to be exact. It's a model. So it's okay to get 2 values for t's. Only one of them is our actual value. Because when we factor this, we get one of the values of t being 0, which is again, it's okay. So when I factor out a t, I get that it's t 1/2 gt plus vi sine theta. And that's essentially going to equal 0. One of my times goes to 0. Excuse me. The other equation is set to equal 0. So if I solve for t, I get that time is equal to negative v initial sine theta times 2 over g. So now that I have this time, I'm going to plug this into my horizontal equation for time to figure out how far that ball is going to go. So let's first look at the horizontal equation. We have x final equals x initial plus, let's, instead of writing v initial x, let's write what that is. That's the radius times the cosine. So that's the full initial velocity times the cosine angle times our time, which is what we just found, plus 1/2 ax times squared. Now, I already denoted my starting spot's the origin, so my x initial is 0. I also want to specify one thing. Do I have forces in the horizontal direction? So once it leaves my hand, I'm not pushing on it. There's no air drag. There are 0 forces in the x direction. Or you could say 0 net forces in the x direction, which means there's no acceleration in the x direction. This is 0. So my x direction, it simplifies quite a bit, especially since I have to plug in that fun formula we just found for time. All right. So x final is equal to v initial cosine theta. And then this is all being multiplied by this new time value I found down here, right? So I'm going to plug that up here. Negative v initial sine theta times 2 all over g. So we can simplify some things a bit. I get x final equals, let's pull the negative out. That becomes v initial squared. Let's pull the 2 out in front too, just to make it prettier. This is going to be cosine theta sine theta all over g. And this is going to be worth most of my points for my equation. That's like all of the points right there. So now that I've got that, we can go about plugging in our numbers. The last letter in our acronym, Phi DESA, is A for answer. We're running out of space here. I'll plug it up right here. So A, answer. This is just plugging in the values right at this point, right? So I'm going to have my x final is equal to -2. My initial velocity, which was the 10 meters per second squared, the cosine 45 times the sine of 45, all divided by -9.8 meters per second squared. So when we plug everything into our calculator, we get that the final position For this ball, for the forces that you got, for the velocity it's set at the angle in which it was thrown, the final position is 10.2 meters. And this means kind of in relation to your friend, 0.2 meters outside of the realm of where he's standing, it's going to hit him. So he will be able to, or he or she, right, will be able to catch the ball just fine. So comparing the distances for answering the question and be like, will they be able to catch the ball before it lands? The answer would be yes. They will be able to catch the ball before it lands.